T1. And this is theta 1, and then remember this was 50 grams, so 0.49, and then this one was 0.2, and then the distance between this and this was 30 centimeters. Then you had, this one was a longer length. 0.49. This was 3 microcoulombs, 2 microcoulombs, and then this one exerted a force like this, F, and this one exerted a force like that, F. This one we called T. This one we called T1. And then this one we call T2, and then at the end we got this equation, T2 sine theta 2. The original 4 equations were T2 cosine theta, so this is theta 2, T2 cosine theta 2 is equal to, that's this one here. T2 cosine theta 2 is F sine alpha plus 0.49. Then you have T2 sine theta 2 is F cosine theta. And then these two are for the other object. F cosine alpha. So for this guy, you have F cosine alpha is equal to T1 sine theta 1. And then F sine alpha plus T1 cosine theta 1. Is equal to 0.49, and then we put them together and we got we eliminated the F and we got these two equations.
So the first one is your sum of the forces in the y, right?
Yeah, this is sum of the forces in the y for this guy.
Okay.
So you're taking it, breaking it up into y. The y of this must be equal to the y of that, okay, plus the y of plus that guy. Okay. Sum of the forces in the y, and this is the x. This is the x and this is the y for this guy. Okay, so x and then the y for this ball, and then this is the y and then the x for this guy. And then when we eliminated it, we got this one, 2 sine theta 2 is this one, we substituted this here, T1 sine theta 1, and then we also eliminated that one, and we got T2 cosine theta 2 plus T1 cosine. Is 0.98. So now, to make this problem doable, on Monday when I was doing it, I said let the length here be 30 centimeters, and then you should technically be able to solve yeah, you should be able to solve these, but there's so many unknowns. So the better way to do it, to make it a little bit more doable, remember when they were the same length, we first solved this problem when they were the same length, and then we got the same angle and we got 26 degrees before doing this. So now the problem can give you one of the lengths, not give you the other one. Let's say we call this L, So now, then we could give you the two angles. Say, okay, this one experimentally, let's say you did it, and I've done this problem already. I worked it out to see if it's how it comes out. So if I give this angle 28 degrees, so I'm giving it an angle greater than when they were the same length. Remember, it came out 26. So I'm giving it slightly bigger angle, and then this one I'm going to give it slightly less angle than they were when they were the same. So I'm going to give it 22 degrees. So I'm expecting this one to come out longer, okay? Longer than 20 centimeters, because the longer one wouldn't go up as much, okay? The shorter one would go up more. So I'm saying if this is 28, 22, can we solve for L? And can we solve for the tensions in the strings and all that? Well, the tensions in the string becomes an easy problem, because then you can just, if you know the two angles, then you just have two unknowns right here. So that becomes a very easy. T2 sine of theta 2 becomes 22 degrees. T1 sine 28. Right, and then this one becomes T2 cosine of 22 plus T1 cosine 28 is 0.98. This one you just do a simple substitution, right? So for T2, plug it into here, and then you can solve for T1. So T1 and T2 becomes very easy to solve. So substitute and solve for T1 and T2. Okay, but more interestingly, now how do we solve for the L? Okay, to solve for the L, here is what I did. Oh, okay, I went back here and I said, I took, let's say, equation 1 and 2. You could either take these two or take these two. And then I would say solve for T2 and then plug it into this T2. So you only have F, you see? So that's kind of what I did. I said, take this one here, T2 is gonna be F cosine alpha over sine theta 2, right, from there. Then plug it into that T2. And then get rid of T2 from that equation.
What was your angle alpha again?
The alpha is the angle, the line of sight looking from here to here. So it would be this angle here. Alpha. Good question there. So. Alpha, which is also this. When they were the same length, it would go up to the same, and alpha would be 0, because they're at the same elevation. But if they're different lengths, goes like this, then one is looking up at the other, and the other one is looking down at the other, you see. So the alpha is now not 0. So this is alpha, and then this is also alpha. See. So now I take that, solve for T2, substitute it into that T2, then what do I get here? Then this becomes what? F cosine alpha cosine theta 2 divided by what? Sine theta 2. is equal to F sine alpha plus 0.49. And then the cosine can come underneath the sine and make it a tangent, right? So then I can say F cosine alpha over tangent of 22 is equal to F sine alpha plus 0.49. So I'm gonna erase this now because T1 and T2 are easy to solve for. So now I can then take this and put it here, and I'll have factor out the F. Then I'll have cosine of alpha over tangent of 22 minus sine of alpha. So taking this to the left, right? And that's equal to 0.49. Okay, now we do the geometry of this. Okay, we say, okay, what's alpha? So now the distance between the two charges we call R, okay? And then alpha is gonna equal, let's see here, let's calculate this distance. From here to here is gonna be 0.2 times sine of 28, right? Just this piece of the triangle. So that becomes from here to here, it becomes 0.2 sine of 28. The reason I write it down here is because I'm focusing on this triangle here, right here. And then so whatever that is the same as this, right? So if that's 0.2 sine 28, and this is also 0.2 sine 28. I already know from here to here is 0.3. And then what's this gonna be? It's gonna be L sine 22, which I don't know what L is. L sine 22. So now I can add these 0.3 to 0.2. That one at least I could add because I could get a number, right? So when I added that 0.3, I add that to 0.2 sine 28, I get 0.3939 plus L sine of 22. So that's the distance from here to all the way to here, okay? And now I need an expression for this distance. Okay, so what's that gonna be? I do this distance is gonna be L, it's gonna be 0.2 cosine 28, right? And then this whole distance from here to here is gonna be L cosine 28.
22.
I mean 22, L cosine 22. Right, so all the way from there to the bottom, and then from there to here. So the difference of that and this is gonna give me that thing. So this is gonna be L cos 22 minus 0.2 cos 28. And then the 0.2 cos 28 comes out 0.1766. So L cos 22 minus, this thing comes out 0.1766. Okay, so since I don't know L, of course, I don't know what that distance is, but at least I can get an expression for it. So from here to here, it's L cos 22 minus this, and then from here to here is this plus this. So now I can get an expression for the force between the electrical force between the charges. That's gonna be K Q1 Q2 over, right, the distance squared.
Professor, how'd you get the tangent again? Because
Yeah, so cosine over sine is cotangent, but the calculator doesn't have a cotangent button. So I'd rather have a tangent. So then to get a tangent, you take the cosine and bring it under the sine in the denominator. It's like I'm saying 5 over 3, let's say, is equal to 1 over 3/5 mathematically. You see? So cosine over sine is equal to 1 over sine over cosine, and then 1 over tangent. Yeah. Good question. So now I'm gonna have 9 times 10 to the 9th. The charge is 3 times 10 to the minus 6, 2 times 10 to the minus 6 over r squared. So what's r squared gonna be? Okay, we could get an expression for r squared. It's this thing squared, L cosine 22, plus this thing squared, right? So it's gonna be L cos 22 minus 0.1766 quantity squared plus L, 0.3939 plus L sine 22 squared. Then go like that. So that's gonna be r squared times this. Now what's cosine alpha gonna be? Cosine alpha is gonna be, again, one of these, right? One of these divided by r, right? So instead of dividing it by r squared, I'm dividing it by r, which means I'm dividing it by the square root of this number, right? This is what that means. So I could go, so cosine alpha is gonna be this thing, 0.3939, plus
L sine 22.
L sine 22 divided by tangent 22, or let me just write it as r for now. Okay, minus, and then sine of alpha is gonna be L cos 22 minus 0.1766 over just 1r. Okay, and then there's no tangent there. And that's all of this is equal to 0.49. So then when we can factor the r out, so when we factor the r out, what's gonna end up happening? Since r is just the square root of this, and this is the r squared, what ends up happening? Becomes to the 3/2 powers, right?
Yeah.
Because when you go like something like this, 1 over r x squared times, let's say, x, that's gonna be 1 over x cubed, right? But then the x is the square root of, think about it this way. Let's say you've got something like this, a, b, c. C squared is equal to a squared plus b squared. C is equal to square root of a squared plus b squared. Okay, so now if I have 1 over c squared times c, okay? So then you're gonna have 1 over a squared plus b squared times square root of a squared plus b squared, and that's gonna be 1 over a squared plus b squared to the 3/2. And we're gonna see that form occurring quite a lot in our E&M problems. That 3/2 is gonna pop up quite a bit. So this is not the first time or the last time. So you're gonna see that happening. So then that r can just come out, make this a 3/2. And then the rest of this, I can just put it in solver. So just simplify this, 10 to the minus 6, 10 to the minus 6, 10 to the 9th, that's gonna be 9 times 3 is 27 times 2, 54 times 10 to the minus 3, which is 0.054. 0.054. So 0.054 divided by this whole thing to the 3/2 power times this thing, this over this minus this equals 49.49. So I put that into my TI solver. Again, make sure that your solver is in degree mode.
I don't have it.
So I'm gonna save this image on my desktop. Then blow it up so you can see.
Nice and sleep.
So on the TI 89, after you put the equation in like this, and you press enter, it gives you this way of looking at it. So you can kind of really nicely see if you put it in right. It says so 0.054 over tangent 22.
Should it be on
Oh, okay, you know what, I distributed the 0.054 here, over tangent 22 times 0.3939 plus x, okay? And then the next picture, let's see if I did this right.
So many numbers.
Do you have your 89?
Yeah, that was gonna use. Oh my god.
Yeah. So basically, I just multiply this in, 0.054 times this thing, tangent 22, minus 0.054 times this, right? So let's follow, see, everything looks good. And then the next picture has the rest of that, it's here. Okay, so I have 0.054 times tangent 22, plus x sine of 22, right? Minus 0.054 times what? Then I have 0.054 x cosine 22, x cosine 22, and then the next picture has x cosine 22 minus 0.766. And then on the bottom, look what I have. Follow the bottoms. I've got 0.3939 plus x sine 22 squared plus x cosine 22 minus 0.1766. And then this one, 0.766 squared to the power of what? 1.5. See? To the power of 1.5 is 3/2. You see? And that's equal to what? 0.49, right? And then comma x means so for x. Then I did it, it gave me two solutions. And the x is the length of the string. One of them is negative 0.24. So L came out negative 0.24, which doesn't make sense. The other solution, 0.27 meters. 0.27396. So that's 27.396 centimeters, right? If you go back to centimeter. So 0.27 meters Yeah, 27.396 centimeter. Yeah, so that makes sense because originally I had them both 20 centimeters, right? So now if I make this longer, like such as 30 centimeters or something, it's gonna go less angle. So it does work out.
So all you do is distribute the one on the left to the one on the right?
Yeah, I could have taken the 0.054 out if I wanted to, and then divided 0.49 by 0.054, you know. But I just distributed this in here.
I need to bring that.
So it's kind of a good example of quite a bit of geometry problem. And you're doing the free body diagram, and you're getting an expression for alpha. I think that's the keys. The hard part for that problem is getting the correct alpha. What would have happened if they were joined at the top? If the string was joined at the top? Something like this. And now you were told this is 28 and this is 22. And now ask, what's the length of this? Should it be longer than 27 or shorter than 27? If the strings were pivoted at the same point. In other words, with the same charges, same masses, same angles, would it require the string to be longer?
String to be longer.
Think it should be longer?
Well, the distance between them is longer, so
Yeah.
that means the
The
force
distance between them here
is
is
shorter.
longer?
It's shorter.
Shorter?
So the
they're
force
gonna
would be.
have to
So the
separate
force
more.
would be higher.
Also, the force would be higher, so you're saying if it was 27 centimeters, there's no way that the angle would only be 22, 28. They would repel each other stronger?
Yeah.
Because they're closer together. So you're saying this one would have to be longer
To compensate.
for them to compensate for the fact that they're closer. Okay, I buy that. Okay, then what changes in the solution if the 0.3 is missing? So I guess we can just subtract 0.3 from this. Is that the only place that the 0.3 appeared? Yeah, it didn't appear in this guy, right? It didn't appear in this one because here was the difference of the vertical. Yeah, it looked like that's the only place that it appeared.
Cosine alpha, will be right there.
Yeah, so if I subtract 0.3, this is gonna be 0.0939 instead of 0.3939, right? So then everywhere that my equation is 0.3939, I can change it to 0.0939 and then 0.0939 and then go back and resolve it. change my solver. That's the cool thing about this is the solver is that you can say, what if this had changed? What would have the answer been? Be able to predict and go back, change, make the change, and then see if the answer is matching. Okay, so let's make sure we change it. Divided by. 0.44978. Oh yeah, longer. Yep. So now 44.978 centimeters. Yep.
Okay.
Nice.
Yeah, square.
The science square?
Okay, so what other kinds of cases that you have where you're involved two charges or three charges and you want to find the force between them or the electric field? So let's now define something known as electric field.
Yeah.
That is good.
Let me see.
It's almost there.
Does this make any sense?
Oh yeah.
This doesn't
Then we go to mode.
Electric field. Electric field is defined by the force felt between two charges divided by one of the charges that is at play. So imagine you have here the charge Q and another charge Q, and this guy is exerting a force on that equal to KQQ over R squared. So now I want to know if this charge wasn't there, then this guy doesn't exert the force on anything. There needs to be another charge there to exert force. But what would the electric field be over there created by this charge? You see? So the idea of fields is a way of saying how do two charges exert force on each other? How does this charge even know that this exists? And the idea is that this guy feels the effect of the electric field created by the original charge. The original charge sets up a field there. Then when you put another charge there, that charge feels the effect of that field.
So the field is, I'm sorry,
Yeah.
the field is only created once there's two charges are.
No, one charge by itself creates a field.
And then the force is created between the two.
Yeah, then the force is created when you put another charge there. So you're taking the force felt by that charge Q, dividing it by that charge Q, then you're getting, the answer comes out to be KQ over R squared. You see? So the electric field created by the Q only depends on the charge of the Q, and that's equal to KQ over R squared. Now you say, does it work backwards? The answer is yes. This guy, when this guy is not there, this guy sets up an electric field this way. right? And even if that charge never appears, this guy still creates an electric field. But he doesn't experience a force with something unless you put something there, you see. So then the electric field set up by this guy is K little q over r squared. And then the next things we're gonna learn Monday is, okay, what's the electric field set up by a rod at any point? How about if the rod is twisted into a semicircle? How about if it's not a perfect semicircle, like some kind of an arc? How about if it's a ring? What's the electric field of a ring on the central axial line? What if it's a plate? You know, so once we learn point charges, then we can integrate all those point charges and we can find the electric fields of rods, semicircles, rings. So Monday is when we do a lot of the integration. The same thing that we do, pretty much everything we do in this chapter, you can do in the gravitation chapters. You can say, you have two masses. Okay, this guy attracts this guy with a gravitational force. Now, if this guy doesn't exist, what's the gravitational field set up by this guy over there? You see? And the symbol for gravitational field happens to be the same symbol as acceleration because it is the same thing. You see? So gravitational field, what would you do? You would divide the force by the little m, and you would get gm over r squared. You see? So what would the units of what's the difference between them? The units of electric field would be newtons per coulomb. The units of gravitational field will be newtons per kilogram. Right, but newtons per kilogram, because a newton is a kilogram meter per second squared, when you divide that by a kilogram, you get meter per second squared. So the gravitational field set up by an object is the same thing as the acceleration you experience when you're at the surface of that object. But the electric field is not. Okay? So that's why the symbol for gravitational field is little g, which is the same as the symbol for the acceleration. So what does it mean to say the acceleration at the surface of the Earth is 9.8? Well, it means two things. First, if you drop a ball, it accelerates down at a rate of 9.8 meters per second squared. The other thing, it means that the Earth sets up a field there equal to 9.8 newtons per kilogram. Now, if you put some object there with a mass of 80 kilogram, what's the weight experienced by that? The weight experienced by that 80 kilogram mass is 80 times 9.8, which is the famous equation we use in physics 1, mg. Right? Every time you're doing that in physics 1, you're essentially just using this equation. G is F over m. So you're saying take the force, multiply this m by g, that's the force of gravity on you. Which would be the equivalent of saying, for electricity, it would be like saying, if the electric field set up by this guy is 10 newtons per coulomb, then I have another charge there, Q equals to 1 millicoulomb. What's the force felt by that charge? Right? You would do what? If the electric field is already given to you, you would just do Q times Z. This is the same thing as doing mg. You're doing the same thing, but we're just so used to doing mg and mg that we're like, it's ingrained in us. But now you're gonna be getting used to doing QE, right? So if you're already given E at a certain point, and you are told you're placing a charge there with charge Q, then you just do QE, and then you find the force. So you say 1 millicoulomb times 10 newtons per coulomb. Coulomb cancel. And then 10 times 1 milli is 10 to the minus 2 newtons. So that means that charge experiences a force of 0.01 newtons on it due to this charge. You see. So everything that we do for electric field can be done with gravitational field, such as once we find out how to find the electric field of a rod, you can find the gravitational field of a rod. You know, same techniques. The integration techniques, everything is the same, except you're replacing KQ by GM, right? You're replacing it by the gravitational constant and the mass of the planet versus the Coulomb's constant times the charge, okay? So let's imagine now a two-charge situation. Let's say 2 nanocoulombs, and then let's say this is -7 nanocoulombs, and then put it on the number line somewhere. So let's say this is -20 centimeters, and then let's say this is 30 centimeters. Okay, and let's say we can ask what kind of questions we can ask about this scenario. What's up? So 2 nanocoulomb, -7 nanocoulomb. How many different kinds of questions can we ask? Well, we could ask a bunch. First, we can say, what is the total electric field created at the origin due to these two charges? B, where on the x-axis is the electric field equal to 0 due to these two charges? C, where on the x-axis is the electric field, or we should say, where on the x-axis is the electric field, or where on the, I'm gonna say, where on the line, where on the, where on the x-axis between the charges is the E field, its minimum value, and what is that equal? E, where on the x-axis Where on the x-axis is the E field equal to twice its magnitude at the origin. And then E what is the total force of these two charges on a third charge, -3 nanocoulombs, placed at 1/4 centimeters? So these are all electric field or electric force type questions that we can ask about this. Later on, when we get to the equipotential voltage and electrical potential energy chapter, which is 2 chapters later, we can come back to this question and ask what kind of energy equations, what kind of energy questions can we ask? So we can say, what is the total voltage at a certain point created by these two charges? What's the total, where is the total voltage equal to 0? You see, those are different questions. Those are voltage and energy questions. We can say, what's the potential energy of these two charge problem? What would happen if I release them? Well, they would come and collide. What would their velocity be? You see, those are all questions that goes in that chapter. You see, velocity questions, voltage questions, and energy questions. This chapter deals more with forces and electric fields. So if you combine the two, you can ask a bunch of questions, you know, like 10 something questions. So remember one of the simulations that I showed you earlier on the website. There is one good one, the physics, the PhET simulation. This one, there is one that we could almost kind of simulate this problem. You can go to the electricity one. There's a couple of cool ones here that you can almost have a game with.
Oh, you should set up circuits.
Yeah, I'm gonna do when we get to the circuits chapter. This one is a kind of cool one. I'll just show it to you quickly. Electric field hockey. So the idea here is that
Oh, they're on top now.
oh yeah, okay, so here's what you're gonna do. You're gonna do so the idea behind this is that you are given a positive charge and you can put as many positive and negative charges in this field so that you can push this. Once I play start, those charges are gonna be stuck in place, and you're gonna push this so that you make a hockey. You make this hockey puck in there.
The first two charges are positive and negative.
Yeah, that one is a positive charge. So it's kind of like a nice game. You can go. See how they're showing you the electric field created by them? This is the positive charges create electric field away from it. And then this is also positive charge creates electric field away. You see? So now this guy is gonna feel the force of that electric field and it's gonna be pushed, right? Then when it sees another positive, it's gonna be repelled by that, you see? So it's gonna probably go like this, and I'm hoping that it would go like this and go in that direction, you see? Oh, okay. I need to move this. Oh, okay, okay.
Maybe like that.
Okay. Well, it should say congrats. Did I hit the edge?
Yeah, I hit the edge of the.
Ah. Maybe we should look at the VAR, VAR.
Zinger.
Ay! God, this is fun. Lewandowski. Okay, nice. So yeah, you see that? Now that's the MLS. This is the Serie A, Italian league. Much harder to score a goal. Now how many what the hell? Like, what am I gonna do? How am I gonna get that over there? I guess maybe put this here. I have to push this over there, but maybe put a negative charge over there. See, the negative charge creates an electric field towards it.
Kind of like a vacuum, right?
Yeah, vacuum. Maybe put another, but then I don't want it repelling too much. Maybe something like this. Run it. Put another one here. Too strong. Okay, that won't curve it. Maybe I don't need to. Let's see. What if I put the feet here? So you can see how this is so. So how are they figuring this out? Well, at each point, they're summing up the electric fields created by all of them. And then that gives you the total force on that, which gives you the acceleration. So you basically use the laws of kinematics, then keep adding, then the object moves at a certain distance, then find out the total electric field there, that gives you the force on it there, which gives you the acceleration there. So you put this into the program and it can kind of simulate the path that the object will take, right? Pretty complicated. Another simulation here is this one. No, not this one. What was this one? This one's kind of cool because it shows you what happens when you put charges and you allow them to actually move, and they're repelling each other and bumping off the walls. So this is kind of what happens in a gas, right? It goes back to the thermodynamics chapter. They're repelling each other, they're bumping off the walls. So now if I add more charges, charge this doesn't move at all. Okay, go, yeah. So this is all I think this is all positive charge. Properties. Oh no, maybe they're all negatives. It says the charge is -1. I can make them heavier.
Or you could like turn one of them just.
Yeah, it allows you to make the charges different here in this corner. Oops. It allows you to make the charges different, but they're all the same. I guess I could make them positive. But it's not gonna make a difference whether they're all negative or positive, right? Yeah. But it's kind of nice, the dynamics of that, what happens when they're allowed to all exert, not only exert force on each other, but all of them are allowed to move. This is called the many-bodied problem. It's very hard. They're all moving. In the other case, that the hockey game, the ones that I was putting, they were fixed. Only the hockey puck was allowed to move. That's a bit easier, because then you can say the fixed ones create a fixed electric field, and then the other one follows the electric field created by the fixed ones. But here, none of them are fixed. So each one is exerting a force and each one is moving. So to do this problem, like more to simulate it, ooh, it's not easy.
Continue adding, see.
Yeah, let's add. Okay, let's add.
Looks like a fraction.
Oh, wow.
Oh, maybe it changed it after you put it negative to positive, and then you added one, maybe it was.
Let me see here, properties.
Because it's too much.
No, I made them all, maybe I made the charge too strong. Let's make it. more-
There's just a lot of electric field going on.
It's a little harsh.
Reset. Okay, add. Let's add Avogadro's number of particles.
Half a dozen.
Oh, external field?
Yeah, there's like an, like.
Oh, I
external
can add
pressure.
an external field to it.
Great.
I'm not sure how I'm supposed to drag this there. But if I add an external field, they're all gonna feel the effect of that field and go to one side of the box. Okay, cool. Okay, the one that I'm thinking of that can be more like this problem that I have is this one here. So it's really cool one. So I could put a grid here, and I could say, okay, we can actually simulate this situation. 2 nanocoulombs, I can grab 2 of these, and then the other one I can grab 7 of those. So, see the electric field created by it? So, I have 2 nanocoulombs here, and then 7 of these. 1, 2, 3, 4, 5, 6, 7.
That's dope.
Huh? It's pretty nice, isn't it? And now I can have a meter. And then what's the distance between them?
That's the group.
In my case, it's 5, right? So, this is centimeters, huh?
It'll be best if you just project it.
Well, we could make it 500